Welcome to another video session on finite element procedure for solving structural engineering problem. In today's video, we are going to look at the application of finite element procedure for solving plane source system by using the normal penalty method. What I mean by normal penalty method is that in my previous video, I also used a penalty approach to solve this cantilever source problem on Matlab. And while using the method, I assume my large support stiffness, which you will add to the global stiffness matrix. I assume the value to be infinity. I use Matlab to modify the global stiffness matrix, where I modify the global stiffness matrix by adding infinity to the support degree of freedom along the diagonal elements of the global stiffness matrix. In this video tutorial, I'm going to solve this same problem using the penalty approach, which is found in so many finite element textbook. So that's why I call it the normal penalty method, because this is the method you'll find in so many finite element method analysis textbook. So in today's problem, we are solving this plane source system using penalty method, the normal penalty method by finite element procedure. The plane source is actually a cantilevered source of overall span of 4 meter, 2 meter span, 2 meter span, 2000 mm, 2000 mm, making 4 meter to 2 span. The height of the source is 1 meter, and the source is supported at one end, so that's why it's a cantilevered source. It's supported at 2 nodes, as you see in the diagram, node 1 and node 4. And on the source, we have a 3 points load on the source at node 2, node 5, and node 6. So we are to use the finite element procedure to solve this problem on Matlab. So when you have a source problem, the first thing you need to do, you need to define your finite element model for the source. Here, I've already done it. What you see on the screen is actually my finite element model for the source problem. What you need to do to define your finite element model, first, you need to number all your elements. Secondly, you need to number all your nodes in the source. And thirdly, you need to also number the degrees of freedom at each node of the source. Fourth, which is also very important, you need to denote your direction of each of the elements. In the source problem you see on the screen, you see red arrows on each element. The red arrow denotes the direction of each element. I've already actually explained what I'm explaining now in my previous video, but doing the explanation again. So I said to define a finite element model for a source system, first we need to number the element. The number of elements can be in any order of your choice. There is no order to it. It depends on you. In this problem, I decided to number this element 1. The numbers in the triangles represent my member number. So this is my element 1. The element from between node 1 and node 2 is my element 1. This is my element 2. This is my element 3, element 4, element 5, element 6, element 6, element 6, element 7, element 8, 9, 10, 11. So there are 11 source finite elements in this structural system. So after we have numbered our source finite element, the next thing you need to do, you need to number your node. The number of nodes can also be in any order. But in this problem, I decide to number this node here, node 1, node 2, node 3, node 4, node 5, node 6. So this is how I number my source system. You can decide to say this node 4 is your node 1, and node 5 is your node 2, node 6 is your node 3, node 1 is your node 4, in any order. But this is how I decide to number the source system to solve this problem. It is your choice. So that is how we number. We need to number each node in our source system. So after we have numbered each node in our source system, the next thing we need to do, we need to number our degrees of freedom. For a source problem, each node has 2 degrees of freedom. A degree of freedom in the horizontal direction and a degree of freedom in the vertical direction. If you see at node 1, these 2 arrows, one arrow pointing in the horizontal direction and the other one pointing in the vertical direction, actually denotes my degrees of freedom. So at node 1, I have 2 degrees of freedom denoted by the 2 arrows, horizontal arrow and vertical arrow. And I number the horizontal arrow degree of freedom 1, you see the numbering here, and the vertical arrow degree of freedom 2. When we are numbering degree of freedom, it is good practice to number the degree of freedom in increasing node number, in increasing node number. Like now, I'm numbering my degree of freedom 1 and 2 at node 1. I will not go to node 4 and say, at node 4, I will say this is my degree of freedom 3 and this is my degree of freedom 4. I will move to the next node number, which is 2. So at node 2, I will also number the degrees of freedom, degree of freedom 3, degree of freedom 4. Each node has 2 degrees of freedom. At 3, I'll move to node 3, I will number it degree of freedom 5, degree of freedom 6. So you number your degree of freedom in ascending order of node numbering. It's best practice you go that way. It's very good practice. You number your degree of freedom in increasing node number. At node 4, I have degree of freedom 7 and 8. At node 5, I have degree of freedom 9 and 10. At node 6, I have degree of freedom 11 and 12. So this is how we number our degrees of freedom for a source system. And in this system, we have 12 degrees of freedom. 6 nodes, 12 degrees of freedom. Then after we have numbered our degree of freedom, what we need to do, we need to define the direction of our element. Why do we need to define the direction of our element? By arrowhead. We define the direction of our element to know the start node and the end node. It is very important. Like for element 1, I chose the direction to point from node 1 to node 2. You see the arrowhead pointing from node 1 to node 2. The direction can be in any order. It can point from node 2 to node 1, but I chose node 1 to node 2. So choosing this direction means node 1 is my start node, node 2 is my end node for element 1. If the direction was in the opposite direction, node 2 will be my start node and node 1 will be my end node. The definition of this direction of elements is very important when solving source problem using the finite element procedure. The direction is your choice. So, but for me, in this problem, I'm assuming this direction. For element 2, I'm also assuming the arrowhead pointing from node 2 to node 3. So it means for element 2, my start node is node 2, and my end node is node 3. Let's pick element 10. For element 10, the arrowhead, I define the arrowhead pointing from node 3 to node 4. This is the arrowhead there. It's pointing from node 3 to node 4. So it means that node 3 is my start node, while node 5 is my end node. So you define the direction for each of the elements. It is the last thing you need to do when defining your finite element model for a source system. So this is what you need to do when you are defining your finite element model for a source system. So after we have done this, after we have done this, um, we can now move to the Matlab environment and start defining our local stiffness matrix, defining our global stiffness matrix, calculating the displacement vector, calculating the internal force, and all that. So for this problem, I would like to draw our attention. Each element has a constant cross-sectional area of 20.7 times 10 minus 4 meters square. And the Young modulus, denoted by E, is 205 times 10 raised to the power 6 kilonewton per meter square. This is also equivalent to 205 gigapascal. So you should note this. So now that we have defined our finite element model, the next thing you need to do is to compute your local stiffness matrix. And I've already showed you this formula in my previous video. This is the formula. This is the formula for the local stiffness matrix of the Truss element. We need to compute this formula for each of the level elements in our finite element model for the Truss problem. And if we check the formula, what is in the formula? We have ARK. This A is actually denoting the cross-sectional area of the finite element. The EK here is denoting the Young modulus. The LK is denoting the length of the element. While in the metric we see cos theta, sin theta, cos square theta, all that. The theta k is denoting an angle which is measured from the start node of each element. For this problem, I define let's look at this image here. Looking at this image, we have an element called K. It has two nodes, node 1 and node 2. For this first one here, I denoted the arrowhead. See the arrowhead pointing from node 1 to node 2. So because the arrowhead is pointing from node 1 to node 2, that means node 1 is my start node. And it means that I have to take my measurements, my theta angle from the start node. For this problem here, the arrowhead is pointing from node 2 to node 1. We see the direction of the arrowhead pointing from node 2 to node 1. That means you have to take your theta measurement, which is found in this matrix equation. The theta k, we need to compute the theta k from node 2, just because the arrowhead is pointing from node 2 to node 1. So this is the importance of defining this arrowhead for each element. So you can see they are the same elements, but because of the direction of the arrow, we take our measurements from different nodes. So this is very important. After this, another thing you need to know, for this problem here, for the first one, in which the arrowhead points from node 1 to node 2, it means that when you have created your local stiffness matrix for the element, we also need to number the rows and columns of the matrix. So because the arrowhead points from node 1 to node 2, that means you will number your degree of freedom at the start node first. So that's why we have at node 1 we have degree of freedom. At node 1 we have degree of freedom 1 and 2. So that's why we have 1 and 2 first. Then at node 2 we have 3 and 4. So this Truss definition is for this matrix, while this Truss definition here is for this matrix. You can see here, because the arrowhead points from node 2 to node 1, it means we will take the degree of freedom at node 2 first. That is 3, 4. That's why we have 3, 4 here. 3, 4, 1, 2 along the column, and 3, 4, 1, 2 along the row. So this is the importance of defining the direction for each element. It defines how you number your matrix. So this concept you really need to understand to be able to apply finite element procedure to solve Truss problem. Yeah, this is also the same formula for local stiffness matrix for Truss problem. As you can see, I to solve this problem on Matlab, I actually wrote a function that can compute the local stiffness matrix for a Truss problem. I've actually showed you this in my previous video, and in that previous video, I used this function. But because I'm using the normal penalty method, I actually need some parameters here. So I modified this function a bit. I modified the function to give me 3 outputs. Here, the function is only giving me 1 output, k. But I've modified the function in this image here to give 3 outputs, k, c, and s, where k is the global local stiffness matrix, c is the cosine angle cos theta. You can see c equals to cos d theta. S is the sine angle sine theta, sine d theta, as defined in the image. So for us to use this function, we need to enter 4 parameters. We need to enter for each element, we need to enter the angle, which I define as theta. We need to enter the length, which I define as length, the length of the element. And we also need to enter the Young modulus and the cross-sectional area of the element, which I denoted as E and A respectively. Yeah. So once you use this function and you enter these 4 parameters, this function returns 3 output variables for you to help you compute the local stiffness matrix, which is K, which is defined by this Matlab line of code here. So the K gets computed for us. The C is my cosine angle and the S is my sine angle. I actually need this parameter to calculate my normal stress or to calculate my axial force for each element. So that's why I want Matlab to return these 2 values for me. So for example, when we use this function, to use this function, I actually use the function in the command window here. I say I use the function name of the function is GSME. So GSME, I gave it 60 as my angle, 60 degree, 2.5 as the length, 100 as the Young modulus, the area 0.1. So when I enter the value, and I also I created a row vector K1, which I labeled K1, L1, M1. So Matlab will return my local stiffness matrix into the variable K1. That is my local stiffness matrix for the first element, K1. L1 is, I'm defining C as L1. So L1, C will be returned to L1, and L1 is equal, you can see that L1 equals to 0.5. S will be returned as M1 because I'm defining M here. I'm defining S as M1 in the command window. So M1, the Matlab returns M1, like M1 is sine 60. So sine 60 is 0.8667. So you see Matlab has returned 3 output variables for me. And these output variables, they are stored in the Matlab memory, which I can use later to compute my axial force after I've computed my displacement vector for the Truss problem. So you need to understand, this is a formula this is a simple trick, the simple formula that I use to compute my local stiffness matrix for each element in Matlab. So moving to the next slide. In my previous video, I didn't show you this formula for computing the axial stress. This is the axial stress formula for Truss elements. So you want to calculate the axial stress in the normal stress, that is the axial stress in the Truss element. You use this formula. The E here is the Young modulus. The L here is the length of the element. This LE, the length of the element. This L is the cosine angle of the element, the cos theta. You see, that's why I modified the my manual function to return C and S, because I need the cos theta and the sin theta. So the L here is the cosine angle of the element. The M is the sine angle of the element. The Q here is a vector. It's a 4x1 vector that contains the displacement quantity in the start node and in the end node. This is what I mean. The displacement quantity in the start node, say this is the element, there are two displacement quantity in the start node and the end node. 1, 2. There's another one here in the horizontal direction and in the vertical direction. So this is like one quantity, this is another quantity 2, this is another quantity 3, this is another quantity 4. So the 4 displacement quantity is this Q, is a column vector containing this 4 displacement quantity in the start node and the end node. I'm going to illustrate this in Matlab working environment. If you are not interested in the normal stress in the Truss element, you can say you are interested in the axial force rather. Instead of normal stress, you can multiply this stress value by the cross-sectional area of the element, which is what is denoted here. You can see I'm multiplying the stress by the area to get the axial force. F is denoting the axial force in the truss element. So you understand this. F is the axial force, A is the cross-sectional area of the truss element. So if I multiply the normal stress by the area, I get the axial force. When we use this formula, they say note that a positive stress implies that the element is in tension and a negative stress implies that it is in compression. So when the value we get for the axial force is positive, we know that the element is in tension, and when it is negative, it is in compression. So this is the next slide. Using the penalty approach, you can also compute the reaction at the support. This formula is a formula that we have used before in our one-dimensional problem. It's also applicable to the truss problem. The minus is the reaction at the support is equals to this formula, C, where C is the large stiffness, which we define in the one-dimensional problem as the largest value in the global stiffness matrix multiplied by 10,000. The Q is the displacement quantity at the node of the support reaction. The displacement quantity at the support reaction. This Q is actually a 2x1 vector column vector, a 2x1 column vector. So if you multiply C by it, you get the reaction. Let's say you have a pin support there, you get the reaction in both the horizontal and the vertical direction. The A is actually, we define in one-dimensional problem, we define A as the gap between the support and between a node and the support. If we have gap problem in one-dimensional problem, we can model it. We can specify it with this parameter here called A. But for a truss problem, this A is like denoting another thing. Say we have settlement of support in truss, in a truss problem. Say there is a settlement when it was loaded, the support moves, say, downward by, say, 0.5 mm. So you can model that 0.5 mm as your A. So A equals 0.5 mm. So if you have settlement as support, we can define that settlement as our A here. But in this problem, we don't have settlement problem, so A is 0. So when A is 0, this equation here reduces to this formula, minus C multiplied by the displacement vector at that support node. So now these are the basic formula and concepts you need to understand to solve a Truss problem. So now I'm going to move to the Matlab working environment where I will show you how to execute, how to solve Truss problem using the normal penalty method, the normal penalty approach. Now we are on the Matlab working environment. So as usual, I created a live script which I use to solve this problem and which I also use to explain how you solve Truss problem using Matlab. So in the Matlab working environment, there are actually two scripts. We have a function script that helps us compute our local stiffness matrix, which I've written here. So this is what I use to compute our local stiffness matrix. Actually, to create this script, what you need to do, you need to go to the Home tab, you click on New Script. When you click on New Script, this interface will open, a new interface like this will be opened for you, an empty interface, where you will type this Matlab code. So this is how you create a function on Matlab. We also have the live script, which we use to run our code. But to create this live script is different from the method approach. It's different from the function creation approach. You have to come to the Home tab and you click on New Live Script instead. You don't click on a New Script. New Script is for function. The New Live Script is for you to run your code. It's a script you use to run your code to solve problem. So you click on this new live script. An empty interface will be opened for you as shown on the screen, where you will enter your Matlab code, your explanation, and all that. So this is the live script I'm using to solve this problem. So this is our finite element model for a Truss problem. I'm not going to waste my time here because I've already explained this on PowerPoint. So the first thing you need to do to solve this problem, you need to determine your local stiffness matrix for all the elements. In this problem, we have 11 elements, 11 Truss finite elements. So you need to compute the local stiffness matrix for all the elements. So, and to do that, I've showed you the formula for the local stiffness matrix before, EA over L multiplied by a 4x4 matrix. And that 4x4 matrix is actually this matrix here, which I'm going to call this function to help us compute our local stiffness matrix. So to use that function, you need to define your Young modulus. I'm using E here is denoting my Young modulus. 205 times 10 to the power 3 Newton per millimeter square. My unit for my calculation for force is in Newton, while my unit for length is in millimeter. So that's the unit I'm using for my calculation. So that's why this is 205 times 10 to the power 3 Newton per millimeter square. The A is denoting my cross-sectional area of the Truss element. So the A is 20.7 times 10 minus 4 meter square. But because I'm using millimeter, I have to convert the meter square to millimeter square. So that's why I multiply by 10 to the power 6. So this A is in millimeter square. The A is in millimeter square. I'm denoting my angle for element 1 as θ1. You see it? And θ1 in our problem, θ1 is the angle for element 1. And since the arrowhead is pointing from node 1 to node 2 for element 1, that means I'll take my angle measurement from node 1, and since the element is completely horizontal, lying along the positive horizontal axis, that means theta is 0 for finite element 1. So that's why θ1 is 0 here. So the length L1 here is denoting the length of my first element, of my first Truss element is 2000 mm. It's defined here as 2000 mm. So 2000 mm. So I'll run the function we created, and I'll tell it to return 3 output variables, which I'm defining as K1, L1, and M1. where K1 is my local stiffness matrix for element 1, L1 is my cosine angle for element 1, M1 is my sine angle for element 1. So I enter these 4 parameters in the function. So Matlab, and when I write this code, I click on run function, this run button here. So the Matlab code will run and it will calculate my K1, L1, and M1 for me. I can see, you see the K1 matrix, the 4x4 matrix. You see L1 equals to 1, that is cos 0 is 1. M1, that is sin 0 is 0. So this is calculated and is stored in the Matlab memory. So these three output variables are now stored in my Matlab memory. So you do the same thing for all the elements. You do the same thing for element 2. You define the angle. The angle here is defined as theta 2. L2 is the length of element 2. So if I should enter this parameter theta 2, L2, E, and A, and I tell Matlab to return the value as K2, L2, M2. So my local stiffness matrix will be calculated, the cosine angle for element 2 will be calculated, the sine angle for element 2, which is noted here as M2, is also calculated. We do the same thing for element 3, do the same thing for element 4. So this is what you do for the 11th, for all the elements from element 1 to element 11. Let me quickly explain the last element one more time. So theta 11 here is denoting my angle for element 11. And let's see what element 11 is in our diagram. Element 11 is between node 2 and node 6. And the arrow head is pointing from node 2 to node 6. So our start node is node 2. So we need to take our measurement from node 2. So our theta is the angle between element 2 and 11. And that angle is equals to the arctan of 1 over 2. 1000 over 2000. The arctan of 1000 over 2000. So that is the angle here. So this function, this A tan D means arc angle. And to return the angle, no, 11th element. The A tan D means arctan. So this D means is going to return the angle value in degrees. If you don't put D, your angle will return in radians. So you can see 1 over 2. So that is the angle for element 11. So L11 is the square root of 2000 square plus 1000 square. This is a square inbuilt function, square root function. So Matlab returns K11, L11, M11 for me when I enter these 4 parameters. So we define our 11 finite Truss element in this manner. The next thing we need to do, we need to now define our global stiffness matrix by assembling all the 11 local stiffness matrices into one matrix. So to do this, I usually create a base matrix, which is a zero matrix, a zero square matrix. And for this problem, because we have 12 degrees of freedom, that means our base matrix will be a 12 by 12 matrix because we have 12 degrees of freedom. So this Matlab line of code creates a 12 by 12 zero square matrix. So this is square matrix. I define that square matrix. I am storing that square matrix in a variable called K. So this K is what is denoting my global stiffness matrix. So this is my base matrix in which I will add my local stiffness matrix. So we need to now add our local stiffness matrix from K1 to K11 to this zero matrix. I need to run this code. So we see this is a 12 by 12 matrix, 12 by 12. So what we need to do now, we add K1 to our base matrix and we use this Matlab line of code, this simple line of code to do that. Because K1 is located between node 1 and node 2 and the degree of freedom between node 1 and node 2 are 1, 2, 3, 4. Let me show you. Element 1 is located between node 1 and node 2 and at node 1 and node 2, the degree of freedom are 1, 2, 3, 4. And you start your numbering from the start node. So that's why I'm saying 1, 2, 3, 4. So that means that's why we have 1 column 4 here. This 1 column 4 means 1 to 4. 1, 2, 3, 4. 1 to 4. So 1, 2, 3, 4 along the row, 1, 2, 3, 4 along the column. I want to write K1 in that position. So you write this code there, you repeat the same thing here, and you add K1 to it. So that's how you add K1 to the zero base matrix. So you do the same thing for K2. K2 is located between 3 to 6, 3, 4, 5, 6. So you add K2 to the zero matrix. K3, the same thing, is located between 7 to 10, 7, 8, 9, 10. So you add K3 to the base matrix. You can see K3 is added. Let me show you where K3 is added. 7 to 10. Where is 7? This is 7 to 10. 10. So this is the K3 matrix. This is the K3 matrix added to the base matrix. You do the same thing for K4, for K5, for K6, for K7. But if you note something for K6, because the numbering are not the same, we have 3 column 4, comma 9 column 10. The degree of freedom at element 6 are 3, 4, and 9, 3, 4, then 9 and 10. They are not in ascending order like 3, 4, 5, 6. So that's why you write it in this form. And we need to write it in a square bracket. So this 3 column 4 means 3 and 4. This 9 column 10 means 9 and 10. So you write this in a square bracket, you put comma, you repeat the same thing in a square bracket, and you write everything on the left hand side, on the right hand side, plus K6. So this is how you do it. So you do all this for the 11 local stiffness matrices. So after we have done this, now we need to determine this is our global stiffness matrix. Now we need to determine the largest, we need to apply our boundary condition by, and to do that using the penalty approach, we need to add a large stiffness at support degree of freedom in the global stiffness matrix. So in my previous video, I assumed that large stiffness was infinity, but in this video, the stiffness is a large value, and that large value is the largest component value in this 12 by 12 matrix multiplied by 10,000. We don't need to worry that how will you find the biggest value in a 12 by 12 matrix. We can use an inbuilt function called max. So max, you can see the line of code there. I'm using a max function to determine the maximum function value in this K matrix. So if you use this max inbuilt, this Matlab function called max inbuilt function, if you should enter the input variable, the K matrix, you should write it in this form, K then bracket double colon. So this function, this will look at the K matrix and it will return it will calculate, it will compute, it will return the largest value of the global stiffness matrix. So C is that value multiplied by 10,000. So this is how I compute the large stiffness. So the large stiffness, when you run this code, you get 7.2799 times 10 raised to the power 9. So now this C, we need to apply this C to our support degree of freedom. And for our Truss problem, let me go to the image. For our Truss problem, we have support at node 1 and node 4. And the degree of freedom at that node 1 and node 4 are 1, 2, 7, and 8. So we're adding support and the C at 1, 2, 7, and 8 of the global stiffness matrix. That is along the diagonal of the matrix. So because we have a degree of freedom at degree of freedom 1, so it means at 1 column 1, at 1 comma 1 of the global stiffness matrix, we need to add C. So this Matlab line of code does that for us. So you can see K1 comma 1 equals to K1 comma 1 plus C. We see, so C is added to this position at 1 comma 1. So we also have support degree of freedom at node 2. So at 2 column 2, we need to also add C. So C is added at this position for the degree of freedom at node 2. We have a degree of freedom at node 7 and 8. So that's why it is 7,7. And with 7,7, when you run this code, this is 7,7. C is added at this position. The same thing for the 8th degree of freedom at 8,8. This is 8,8 here. So C is added. So this is how we modify the global stiffness matrix with the large stiffness. So this is the final modified global stiffness matrix, and this is what we need to invert to compute our displacement vector for the 12th node in the Truss problem. So after we are done with the global stiffness matrix modification, we need to now determine our force vector. And the force vector is like the list of the forces along each degree of freedom. The force vector is a 12 by 1 matrix for this problem because we have 12 degree of freedom. So in this problem, we have 3 loads. One node at node 2, node 5, and node 6. At node 1, we have 0.5 kilonewton, 2 kilonewton at node 5, 1 kilonewton at node 6. Because the unit I'm using in this Matlab is in Newton, so I need to convert this force unit to Newton. So I multiply by 1000. So that's why you see minus 500 here, minus 2000 here, and minus 1000 here. And I'm adding this value at this minus 500 is at the 4th location in the matrix because the load is along the 4th degree of freedom. It's vertical in the at the 4th degree of freedom, and it is pointing downward. So I'm taking downward force as negative. Also at node 5, the degree of freedom there is number 10. At node 5, the degree of freedom is 10. The load is pointing in the 10 degree of in the direction of the 10th degree of freedom. That's why we have minus 2000 at position 10 of the matrix, and we also have minus 1000 at position 12. At position 12 degree of freedom of the matrix. You can see 1 kilonewton is pointing downwards, so we have minus 1000 at position 12. At other nodes where we don't have load, we denote it as 0. So that's why we have 0 at other position. So when we run this code, well, we need you know something. I also use an apostrophe here to convert this row vector to a column vector. So that's why we have a vertical column number, a vertical column vector here. So this is our column vector. This is our force vector. So now we have defined our force vector. We can compute the global stiffness matrix simply by inverting the modified stiffness matrix, which we have created, which we have defined as K by our force vector, this vector here, PS. I'm defining the force vector is the PS variable. So we multiply these two variables together, we get our displacement matrix. The DS here is denoting my displacement matrix. So these are the displacement vector for the matrix. If you notice at degree of freedom 1 and 2, we have the value there is supposed to give us 0, but it's giving us something like minus 0.0000 something. A very, very small value. It tells you that the finite element procedure is not an accurate method, it's an approximate method. It's an approximate method. So we are not getting exactly 0 there. We are getting a very, very, very small value. This value is very small. But we can use this small value to calculate the reaction at the support. That's the interesting thing about the penalty method. So the displacement vector you can see at 3, 4, 5, 6, 7, 8, 3, 4, 3 to 6. You can see the displacement vector. At 7 and 8, we also have support degree of freedom. You can see is 0.0000 something. But Matlab writes it in 4 decimal place, but actually a very small value. At 9 to 12, we don't have support degree of freedom there. You can see the value there is quite significant. So this value is in millimeter. This is our displacement vector in millimeter. So once you have done this, this is our global displacement vector. You can calculate your local displacement vector for each element simply by extracting the displacement at the degree of freedom, at the degree of freedom in the computed global displacement vector. So I use this Matlab code here. This ds1 is denoting my displacement vector for element 1. And we already know that ds is our global displacement vector. So because element 1 is located between 1 and 4, so 1 column 4, I input it here. So Matlab look through the global displacement vector and returns these 4 values for me, 1 to 4. 1, 2, 3, 4. So you can see that's what is returned here. It's the same. For element 2 is located between degree of freedom 3 to 6, 3, 4, 5, 6. That is at this point 3, 4, 5, 6. So these elements, these values are returned, are calculated here for element 2. So you do this for all the elements. Do this for all the elements. So once you have calculated the local stress metrics for all the elements, next thing you need to do, you need to determine the normal stress for all the elements using this formula. In the formula, as I already explained, E is the Young modulus, LE is the length of the element. The L here in this square bracket is our cosine angle. The M is our sine angle. I already computed that when I was computing the local stiffness matrix for each of the elements. I define L and M for each element, like L1. For L, I define L1 to L11. For M, I define M1 to M11. So these values are already stored in the Matlab memory. You can just call them out easily, use them easily now. So we use this value for the normal stress. But if you are not looking for a normal stress, say you are more interested in the axial force, you multiply this stress value by the cross-sectional area. So this multiplied by cross-section, this stress equation multiplied by the cross-sectional area will give us the axial force. So this is what I did here. The F1 is denoting the axial force for element 1, F2 is denoting axial force for element 2, to F11. I computed the axial force for all elements using this stress formula multiplied by the area. So you can see E is the Young modulus, L1 is the length of the element of element 1, which I already defined. This small letter L1 is our cosine angle for element 1, M1 is our sine angle for element 1, which is already computed, so you just need to enter them here in the bracket as specified in this equation, multiplied by Q. This Q here is a 4x1 displacement, local displacement vector for the element. So for element 1, I already defined the displacement vector as ds1. That's why I calculated the displacement vector for each element and before computing the stress. These are the displacement quantities for element 1, which we can use, our Q, which we can use here, ds1, multiplied by the area. So this is the area which we define this area in our first line of code at the beginning. So once you write this code and you click on run, you see the area force gets calculated, minus 5.4634 times 10 to the power 3 Newton. You do the same thing for element 2. You define the area force as F2, E, L2. You see L2, I'm using L2 here, the cosine angle for element 2, sine angle for element 2, multiplied by the displacement vector ds2, which I've already defined in the code above, multiplied by A. So this you do this for F2, do this for F3 to F11. As you can see, this F1 is minus 5.4634 times 10 to the power 3. This minus means this element is in compression. And you can see I denoted it in my diagram here. This element 1, you can see the force is there. The force is defined as a compression force. 5.46 kilonewton in compression. You can see the direction of the load at the node is pointing towards the element. So it means that this element is in compression. So this is 5.46 kilonewton, and which is which is exactly the same with our final element result, minus 4.46 times 10 power 3 newton. So this is minus 5.46 kilonewton. Here element 2 is minus 0.938 kilonewton, minus 0.939 kilonewton. So which is also what we have here, 0.94 kilonewton compression. You can see the direction of the arrow, compression. So everything is the same. So this is how we define this is how you define this is how you use finite element procedure to determine the axial force in the element. I want to draw our attention to element 5. Element 5 is supposed to give us zero force. When we check the F5, the axial force in element 5, which is this F5, you can see it's giving us a very small value, 0.0021 newton. In kilonewton, it will be 0.000021 newton, a very small value. It tells you that there's a margin of error while we're using the finite element method. It does not always give an accurate answer. So here we have a very small margin of error, as we see here. So it's giving us like 0.0021 newton, which is supposed to be 0. So you should note this. F5 is supposed to be 0, but it's giving us a very small value. I want to also, so you do this, so this using this axial force, you get the axial force, the force in the element direction for each element. Like for element 8, here I define the horizontal and the vertical component of the force. Element 8, we should check element 8. Element 8, the force is 3.872 times 10 power 3 newton. That is the resultant force at element 8 in tension, 3.872 kilonewton. If you see the element here, one is 3.46, one is 1.73. The resultant of these two forces is 3.86 something kilonewton. So you can see that the finite element procedure is a very powerful method for solving Truss problem. So say we don't want to use this axial stress formula, we can use this formula. The axial force in the local stiffness matrix equals to the local stiffness matrix multiplied by the displacement vector, the local displacement vector of each element. So K1 multiplied by ds1. So we should multiply, we can also get the force component in the x and y direction of the node. You can see we have 4 components for P1, 5.4634 in the horizontal direction at node 1, at degree of freedom 1, 0 at degree of freedom 2, minus 5.4634 times 10 power 3 at degree of freedom 3, at degree of freedom 4, 0. So this is like a compression member. So as you can see, you can do this for the 11th element. So this is how so there are two ways of computing the axial force. Either you use the stress formula or you use this formula. The last thing is the computing of the reaction. Using the penalty method, you can compute reaction at support. That is the beauty of using the penalty method, which you cannot do when we use the elimination method. But because we are using the penalty method, we can compute the reaction using this formula. And I have told you in my PowerPoint, we don't have gap problem, we don't have settlement problem. The A is 0. The A here is our settlement. So the A is 0 here. So if A is 0, the reaction component will equals to minus C multiplied by QP. This QP is the displacement quantity at the node of the support node. And in our problem, we have two supports at node 1 and node 4. At node 1, the degree of freedom is 1 and 2, and at node 4, the degree of freedom is 7 and 8. So we need the displacement quantity at 1 and 2 and displacement quantity at 7 and 8 to compute the reaction values. So the reaction value I'm denoting R1 as my reaction at node 1. So I use the formula minus C, which is already computed. I'm just calling it out. I'm now use this is global displacement vector, but I need just the element at 1 and 2, at position 1 and 2. If I should multiply this, I get the reaction force at node 1. So you can see we have 9,000 Newton, that is 9 kilonewton in the horizontal direction, and the vertical reaction is 1.768 kilonewton. At node 4, I'm noting it as R4. We also have two reactions. So we multiply C by the displacement quantity at 7 and 8, that is 7 column 8. We get minus 9 in the horizontal direction and 1.7317 in the vertical direction. Let's verify this result. I have a verification result in my PowerPoint. We'll check it now. So this is actually start pro source analysis results. I modeled this problem on the status software. You can see the reaction component at node 1 as 9 kilonewton and 1.768 kilonewton, which is the same thing with what we got in our Matlab calculation. And also at node 4, we can see the reaction value as minus 9 and 1.732. You can see that the final element result gives a very good result compared to the source result on status software. So this is how we use the normal penalty method to solve Truss problem on with finite element procedure on Matlab. In my next video tutorial, I'm going to explain the same problem using the elimination method approach. So I'm going to explain how we can use the elimination method approach to solve the same problem. Thank you so much for watching my video, and I hope you have learned a lot on the application of finite element procedure in solving Truss problem. You need to actually solve you form a question on your own and try to apply this procedure to solve it, and you compare your answer with software results or with manual calculation. You can maybe sketch a 3-member Truss problem and try to use this Matlab to solve the problem and compare it with your own calculation. See how you see if you can actually apply the finite element method to solve simple Truss problem. Thank you so much for watching my video. Again, see you next time.